this talk, I'll be discussing the topic of human energy expenditure, whether it's constrained, and I'll specifically provide an argument against this hypothesis. I'd like to start by being clear about what I am not saying. I am not saying that I do not respect the work done by those who propose the human energy expenditure is constrained. I do respect the work that these people have done. I'm not saying that exercise is effective for weight loss. There are many reasons why exercise is not a particularly effective tool for weight loss for most people. I'm also not saying that reductions in resting metabolic rate cannot happen. These can clearly happen, for example, with energy deficits, and I'll present some data to show that. But before I begin, I'll define some of the key terms. Energy expenditure can be broken down into several components. Some of these definitions of breaking this down can be somewhat arbitrary, but some of them less so. We might often hear the term resting metabolic rate, sometimes used interchangeably with basal energy expenditure. And this is normally measured in the fasted state once people have woken up first thing in the morning. And this can actually be broken down further into sleeping energy expenditure, SEE, because there's a small increase from sleep to when we're awake, which is provided by that arousal. This is normally measured with indirect calorimetry, or gas exchange measured at the mouth, where we've got oxygen consumption and carbon dioxide production. We've then got other components of energy expenditure that we can sum to get the total. These include a component there of other, which could include things like cold-induced thermogenesis, an increase in energy expenditure when we're exposed to cold, but before we get the onset of shivering. There's diet-induced thermogenesis, or the thermic effect of feeding, and this is the energy we use to digest, absorb, and metabolize the food that we eat. And then we've got activity energy expenditure, or sometimes physical activity energy expenditure. And this is the energy associated with skeletal muscle force production. Normally that's associated with actual movement, but sometimes it's not. So for example, we could do an isometric contraction, such as a plank or a ski sit, and there would be an increase in energy expenditure, but we wouldn't necessarily be moving. So there is muscle force production. Measuring activity energy expenditure can be done in several different ways. One of them can include the combination of accelerometry and heart rate monitoring, and I'll come back to that in a moment. We can sum all of these to get total energy expenditure, or we could use a method such as doubly labelled water to get the total energy expenditure, and that's the gold standard for free living scenarios. We can also get components by, for example, measuring total energy expenditure with doubly labelled water and subtracting others such as resting metabolic rate to deduce, for example, physical activity energy expenditure. And I'll also come back to that later. One other consideration is whether there's a difference between what we mean with physical activity versus physical activity energy expenditure. Physical activity can be considered the external work, i.e. running distance, or step count, or activity count, whereas the physical activity energy expenditure would be the energy that's associated with that. So and that depends on things like efficiency and economy of movement. So what is the energy constrained hypothesis? Well, it's depicted in this well-selling book by Herman Ponzer called Burn. One of the quotes from this we can see says that exercise does not increase our metabolism. Instead, we burn calories within a very narrow range, nearly 3,000 calories per day, no matter our physical activity level. And another quote, the bottom line is that your daily physical activity level has almost no bearing on the number of calories that you burn each day. These are from non-peer-reviewed, non-academic sources, so we could look at some of the peer-reviewed literature as well. So here's a quote taken from a peer-reviewed journal article by Herman as well, where we've got this statement that defines the energy expenditure hypothesis. That increasing physical activity has a limited effect on total energy expenditure and instead leads to a reduction in non-physical activity metabolic activity to keep the total energy expenditure near its set point. So this is positing causality. It's a causal statement. In effect, it's saying that the cause is an increase in physical activity, and that the effect this would have is by reducing metabolic rate and or a maintenance or a less than expected increase in total energy expenditure. Now, when we're considering cause and effect and causal statements, we need to really find evidence that this is the cause independent of things like confounding factors and reverse causality. And the study designs to establish cause and effects really matter. Now, one of the things that could confound this is an energy deficit, because we know that this concept of adaptive thermogenesis is very well established when people are in an energy deficit. These are data from the Minnesota starvation experiment, and they show resting metabolic rate that has been adjusted for the body composition of these people. So it shows that after 24 weeks of semi-starvation, there is a reduction in resting metabolic rate, even when we adjust for changes in body composition. So clearly, calorie restriction can result in a reduction in resting metabolic rate that is greater than we would predict based on the loss of things like fat-free mass. And that means that what we're really talking about with this energy constrained hypothesis is effects of physical activity independent of energy balance. We can conceptualize the energy constrained model in comparison to what we might consider as the status quo. So the status quo of how we consider energy expenditure would be that physical activity energy expenditure adds to other components, i.e. the additive model, to increase the total. So we can see here as we go from left to right, we've got increasing physical activity energy expenditure. The other components remain relatively stable as long as body composition remains stable, and the physical activity energy expenditure directly adds to this. Compare that to the constrained hypothesis, which is the novel one. And being the novel one, we really need to find evidence that is robust in order to reject the additive model. We can see that as we now go from left to right, with an increase in physical activity energy expenditure, we see a reduction in these other components to constrain the total. Now, one final bit before we look at the direct evidence for and against these hypotheses. One thing to bear in mind is the measurement methods that are used to measure these components of energy expenditure. So the gold standard for measuring energy expenditure would be direct calorimetry, i.e. heat production. And when indirect calorimetry has been directly compared to direct calorimetry, it's shown to be very good indeed. These are data from Max Rubner in Small Dogs, where we've got the direct comparison of the two, and you can see that over a 45-day measurement period, they are essentially equivalent. So indirect calorimetry can provide very good measurements of energy expenditure. It can be used for both rest and activity, but the downside is it's typically constrained to a laboratory environment. So if we're going to look to understand this under free living conditions, we need to consider things like wearable methods or doubly labeled water. And the problem with wearable methods is they have much variability in their validity. Here we've got a pedometer compared to indirect calorimetry when measured using activities of daily living. So things like household chores, doing the laundry and hoovering and so on. And we can see that step counts or the pedometer estimate of energy expenditure isn't very good at all when compared to indirect calorimetry. In contrast, other wearable methods can be very good. Here we've got the ActiHeart monitor. So this measures accelerometry at the chest combined with heart rates. And importantly, this can be calibrated on an individual level. So we can take someone's individual heart rate at a given energy expenditure measured by indirect calorimetry to individually calibrate the equation. And when that's done, these devices can provide very good estimates of energy expenditure. So my first summary would be that constrained energy expenditure is a causal hypothesis, and it states that the cause is increasing physical activity, and the effect would be a less than predicted increase in total energy expenditure, which is due to reductions in other components such as resting metabolic rate. We know that there can be a reduction in resting metabolic rate from an energy deficit. That's very well established, and therefore What we're talking about here are the effects of physical activity independent of energy deficit. And finally, the methods of measuring components of energy expenditure display variable validity and show we should consider these methods when we're interpreting the evidence. In addition to the measurement methods, it's also important to consider the study design. Remember, this is a causal hypothesis, and the different study designs are more or less susceptible to estimates of causal effects, to bias in those estimates of causal effects. So if we do no experimental manipulation and no randomization, that would be in the category of classical epidemiology or observational studies, so cross-sectional studies or prospective studies. And these are the most susceptible to bias when we're trying to estimate cause and effect. But let's look at that literature first of all. There's a fantastic database known as the double-labeled water database, where there are measurements of human total energy expenditure across essentially the entire spectrum of human age and body mass. And when we look at these data, we can interpret them in relation to this quote that I've reproduced from earlier on in the presentation, that we burn calories within a very narrow range, nearly 3,000 calories per day, no matter our physical activity level. So do these data support that statement? Here we can see the total energy expenditure in millijoules per day from people under the age of 1 right through to over the age of 90 in men and women, so across that lifespan. And we can see that there's a very wide range, in my opinion. So at the lower end there of the adult range, 1,700 kilocalories per day, and at the higher end of the adult range, 4,000 kilocalories per day. So the range there is over 2,000 kilocalories per day, and in my book, that's a wide range. So some more observational data have been used to support the energy constrained model, again from the double-labeled water database. So here what you can see on the x-axis is basal energy expenditure, and on the y-axis, total energy expenditure. And the authors inferred from this that there was a suppression of resting metabolic rate with an increase in total energy expenditure because this correlation was not perfect. You can see that the slope isn't perfect, it's slightly shifted downwards. And so the authors inferred that as basal energy expenditure is going to the right, the total energy expenditure isn't increasing proportionally. However, there's a problem with this because no measurement is perfect. There is always some degree of measurement error, and so we should never expect a perfect correlation. A lack of a perfect correlation can be completely explained by a phenomenon known as regression dilution from normal measurement error. A second piece of data from this particular study showed a negative correlation between basal energy expenditure on the x-axis here and activity energy expenditure on the y-axis. And because of this negative correlation, it was suggested that there was a suppression of resting metabolic rate with increased activity energy expenditure, again used to support this energy constrained hypothesis. But there's also a problem with this inference, because basal energy expenditure appears in both the x-axis and the y-axis of this figure. You can see that it's appearing in both because how activity energy expenditure was measured was by deduction. They took the total energy expenditure and subtracted basal energy expenditure from that. And that results in mathematical coupling, which just means that that basal energy expenditure appears on both the x and the y components of this axis, and that can generate spurious correlations. And when it's subtracted in this way, that spurious correlation would indeed be negative. We can show that empirically here, because if you simulate data of basal energy expenditure and total energy expenditure that are generated to be completely uncorrelated, when you then deduce activity energy expenditure by subtracting basal from total, then it produces this negative spurious correlation. We can also show with real data collected by Ollie Chinosky-Smith, where independent measures of basal energy expenditure and activity energy expenditure were determined using indirect calorimetry and acti-heart monitors, respectively, that there is a negligible correlation between activity energy expenditure and basal energy expenditure. So it does seem to suggest that the negative correlation reported was a consequence of mathematical coupling. So there is no good evidence from classical epidemiology to support the energy constrained hypothesis and to reject the additive model. Let's move then to a different type of study design which might involve some kind of intervention. So not necessarily randomized, but maybe a pre-post comparison within a single group. An example of this is taken from this Thurber paper, where participants were ultra endurance runners and they were studied before and after this ultra endurance event. What you can see is that they've got predicted energy expenditures, which are broken down into the components of basal metabolic rate, thermic effective feeding, other, and the running activity energy expenditure. And then we've got the observed measurements. Now, one thing to consider is what we might expect constraint to look like. At week 14 there, this is personally how I would expect some kind of constraint to look like if it was substantial. You can see there's a reduction in basal metabolic rate that's constraining the total, aligned with what the hypothesis states. However, when we actually look at the evidence, the data that were collected, you can see that there's no evidence that basal metabolic rate was reduced. If anything, it's slightly increased. And that there is no evidence of a reduction in the non-physical activity metabolic activity. So again, these data do not support that statement. So my second summary is that total energy expenditure of adults often varies by more than 2,000 kilocalories per day. The observational data have several critical limitations, such as regression dilution and mathematical coupling. And prospective field-based studies also do not support a lowering of resting metabolic rate with increased physical activity. But all of these studies are, of course, biased with respect to causal effects because they're not including randomization and experimental manipulation. There is one type of study design that has a degree of randomization, but not necessarily experimental manipulation, known as genetic epidemiology or Mendelian randomization. And I have looked at databases in order to do that analysis, but it seems like some of the largest databases that are available have only predicted resting metabolic rate rather than actual measured resting metabolic rate. And I'd be keen to know if anyone's aware of such databases to perform these analyses. That leaves us then with the combination of randomization and experimental manipulation, which is the randomized controlled trial. And that's the gold standard for establishing cause and effect because it's the least susceptible to bias in these estimates of causal effects. So if we're going to use a randomized controlled trial to understand this hypothesis, then we want to look for randomized controlled trials that have an intervention being an increase in physical activity or exercise compared to a randomized control group. And we then want to see the effect of an outcome being a reduction in resting metabolic rate or a less than expected increase in total energy expenditure. And one important point to consider when we're interpreting randomized controlled trials is what are we comparing? Bland and Altman, the very famous statisticians, have stated that randomized groups should be compared directly. So we should compare those two randomized groups by two sample methods, and specifically that separate tests against baseline are highly misleading. As an example of this with mock data, you can see here a theoretical randomized controlled trial with an intervention and a control group. If you just do that within group analysis, tests against baseline, in that intervention group, it would suggest that there is a zero net effect on total energy expenditure. However, if you directly compare the randomized groups, now you would infer that the intervention has resulted in an increase in energy expenditure of 100 kilocalories per day. And then if you also correct for baseline, so that can be done with covariate analysis or just by subtraction, then the estimated causal effect of the intervention here is now an increase of 200 kilocalories per day. And this would be the most efficient and the least biased estimate of a causal effect. Luckily, that's what most of the studies have done. We can look at evidence from randomized controlled trials on the effect of exercise on resting metabolic rate. This is from over 800 participants, 22 studies, and up to 24 weeks of exercise training versus a randomized control group. And what we can see is that most of the data points are on the right-hand side of the vertical line. That suggests that if anything, resting metabolic rate is slightly higher than in the exercise group than in the control group. This is consistent whether we look at the overall evidence or break it down by the type of exercise, so endurance or resistance type exercise. But one of the things you might ask is whether people actually did the exercise. So we can also break this down into only the studies that clearly supervised every single exercise training session. And what we find here is that the pattern is the same. So most of these studies are on the right-hand side of that vertical line, suggesting that if anything, there's an increase in resting metabolic rate with exercise versus control. And that's despite weight loss in some of these studies and fat-free mass loss. So if anything, you would expect that to have constrained resting metabolic rate. But despite this weight loss, there is no evidence that exercise reduces resting metabolic rate. So that's resting metabolic rate. What about total energy expenditure? Well, there are only 2 randomized controlled trials to my knowledge that have used supervised exercise and gold standard measures of free living energy expenditure, i.e. doubly labelled water. We've got one that was a 6-month intervention, which you can see on the left-hand side, and on the right-hand side, a 10-month intervention. On the left-hand side, 2 modest doses of exercise, and on the right-hand side, slightly higher doses of exercise. And what you can see on the left-hand side is perhaps what we might interpret as a mismatch between the predicted increase in total energy expenditure and the observed increase in total energy expenditure. On the right-hand side, we can see very good matching of predicted increases in total energy expenditure and observed increases in total energy expenditure. If we pool all of these together, then we can make this kind of inference, that a weighted average of all of those conditions in both of those studies suggests that of the expected increase in total energy expenditure, if that was 100% there, then we generally see about 80% of that increase. So some people might interpret this as evidence of compensation. Maybe this is a reduction in RMR that wasn't reported in those studies, or some other component. But what's often not considered is it could be compensation in non-exercise activity. So for example, the supervised exercise could have been done in the morning, and then perhaps later in the day, people were less physically active in other activities that weren't able to be picked up or measured. And that was resulting in a reduction in total physical activity that reduced total energy expenditure. So it's not a compensation in metabolic rate, it's a compensation in behavior that is sometimes seen in exercise training studies. Or it could also be explained by a phenomenon known as substitution. What do I mean by substitution? Well, it's a bit like if we're trying to study the effect of a light bulb on luminescence, and we assume that we're studying that in darkness, when in actual fact, we're studying it in daylight. The analogy here relates to exercise because the light bulb is exercise, the luminescence is energy expenditure, and the daylight there is our background physical activity level. So there's always some degree of background physical activity, and that needs to be accounted for. To illustrate that with actual data, we can see here the energy expenditure of an individual over a 24-hour period. And we could insert a small bout of exercise, a low dose of exercise at a particular time point. We're introducing new physical activity there. We could introduce a larger dose of exercise to achieve a large net effect of an increase in energy expenditure. But importantly, depending on where we insert that exercise can have a big effect on the net increase in total energy expenditure. Because if we put that large dose of exercise at a time point when that individual would have already been doing physical activity, there's now a much smaller net effect on total energy expenditure. And this has been modelled by Dylan Thompson at Bath using data from a randomised controlled trial in over 240 people. And you can see that if you randomly insert new physical activity at random times of day, then on average, you only achieve 40% of the expected increase in energy expenditure because of this substitution effect. If you insert a large dose of exercise, again at random across this period of the day, then you only get 80% of the predicted increase in total energy expenditure. So this substitution effect can completely explain why there is not perfect matching between the increase in exercise energy expenditure in a randomized control trial and the increase in total energy expenditure that's seen. So when we account for substitution and compensation in NEAT, there is also no evidence from randomized control trials that would reject the additive model. So my third summary is that randomized control trials show that increasing exercise does not lower resting metabolic rate, and if anything, it slightly increases. Randomized control trials also show that increasing exercise increases total energy expenditure. The longest term and the largest studies actually show very good matching between those two methods, the predicted and the observed increases in total energy expenditure. But even when this isn't perfect, substitution and or compensation in non-exercise activity can completely account for this imperfect matching. I'll just finish with one final point about energy deficit, because when we're using doubly labelled water to measure total energy expenditure, the thing that we're actually measuring is the carbon dioxide that's produced over the time frame, which is typically 1 or 2 weeks. And in order to get total energy expenditure, we need to then convert that carbon dioxide produced into oxygen consumption. And to do that, we need to know the respiratory quotient. Sometimes that's calculated by determining the food quotient, which is the ratio of carbohydrate, fat and protein in the diet, because when we're in energy balance, the food quotient will equal the respiratory quotient. However, if we are in an energy deficit, that will change things. And if we don't account for that, that could influence our estimates of total energy expenditure. So here we've got data from Josh Bakadios in military personnel during arduous activity, where we've got measures of total energy expenditure from doubly labelled water. If we assume these individuals were in energy balance, this is the average energy expenditure and individual data points that we would see. But these individuals were in energy deficit, as shown by changes in body mass and composition. And we also had all of their food intake because they were provided with food packages. So we know how much they ate and the degree of energy deficit. And when we adjust the respiratory quotient for this energy deficit based on room calorimetry studies, and then adjust the equations for total energy expenditure, then this would increase the estimate of total energy expenditure by more than 350 kilocalories per day. So essentially, if we are studying people that are in an energy deficit but we don't know it, or we don't account for it in the measurements of energy expenditure by doubly labelled water, then we would underestimate the true energy expenditure. So this is something that needs to be considered in these studies. This could contribute to how energy deficits influence the data surrounding this hypothesis, and there's also a second way as well. So how I would view this is that as we increase physical activity energy expenditure and we maintain energy balance by increasing energy intake at the same time, which would be the blue line, then we see no evidence of constraint and no evidence to reject the additive model. However, if as we increase physical activity energy expenditure, we keep our energy intake stable, or we don't increase it sufficiently to match energy expenditure, we're then in a negative energy balance. That would reduce resting metabolic rates, as we've seen from the Minnesota starvation experiment, but it would also potentially influence our measurements of total energy expenditure via doubly labelled water if we don't properly account for that energy deficit. So my overall summary is that non-randomized data of activity and total energy expenditure are limited by statistical and methodological issues. This includes the susceptibility to bias in causal effects, and it also includes things like mathematical coupling and regression dilution. The randomized data also do not support lower resting metabolic rate with increased physical activity, and the randomized data do not support less than expected increase in total energy expenditure with increased physical activity, especially when we account for the effects of substitution and compensation of NEAT. And even if we don't account for that, when we look at the longer term and larger studies, they clearly don't support this hypothesis. So as of now, there is no evidence to reject the additive model. I'd just like to thank everyone I work with at Bath and collaborators further afield.